Again, now we're going to start in our flask with a solution of weak base, and we're going to be titrating in from our burette a strong acid. Okay? Previously, we had looked at these graphs, right? We're going to build one ourselves as we go through and do these calculations here. All right, so let's just think. If we have a solution of weak base that we're starting out with, what do we think our pH is going to be? Higher than 7 or lower than 7? Higher than 7, right? We have a basic solution. And so our starting point here, what we would call our region 1, is just our solution of weak base. No acid has been added. All right, so then what's our strategy for calculating pH in this solution? The same thing that we learned how to do in chapter 17 for a solution of weak base, right? We haven't even done any titration yet. All we have is our flask with weak base in it. So to calculate our pH, we do the pH of a weak base solution, which is what we learned how to do in the previous chapter. All right, and I know you all are experts on this, but let's just go through it to make sure we know. Okay, so now we're going to prepare a solution of a weak base. So let's go ahead and prepare 1.2 liters of a 0.58 molar solution of ammonia. What is the pH? Okay, so this is remarkably similar to where we started our weak acid strong base titration with, right? We got to do the same sort of thing because we're talking about a weak base. We can't just assume that our concentration is equal to the concentration of hydroxide. We got to go the long way and do the equilibrium here. So the first thing we need is our Kb reaction because it's a base. Once we get our Kb reaction, we can build that Kb expression. And what do we use to fill in that Kb expression? An ice table. All right, so especially important here, make sure that you can tell me what reaction we're talking about if I'm saying a Kb reaction. Okay, everybody take a second, see if you can't fill these in, and then we'll do them together. All right, so for our Ka and Kb reactions, we're talking about creating a solution. So we're going to take this weak base and we're going to mix it with water. Okay? Now our base is going to play the role of the base. It's going to accept a proton. All right, and water is playing the role of an acid, so it's going to donate a proton. It's going to go down in number of hydrogens. And so my hydroxide ion is my product of my Kb reaction. All right, if we just want to sort of rewind here, when we take a Ka reaction, it's very similar. We're also mixing our compound with water, but the difference is that we're mixing an acid with water, right? So water is going to gain a proton. And so for our Ka reaction, our product is the hydronium ion. But for our Kb reaction, our product is the hydroxide ion. All right, make sure we got these two fundamental differences down here. In both cases, we're mixing with water, but the difference is what role is water playing. All right, in the case of our Kb reaction, we're mixing a base, so water will play the role of an acid and lose a proton, giving us a hydroxide ion. Okay, very similar, but very important difference, the product that we get. All right, so then we're going to build our equilibrium expression. What do we remember? What over what? Products over reactants. And then, as we said, in order to fill in this expression, we're going to need to build an ice table. All right, now, importantly, what units am I going to use for my ice table here? Do I have to use moles, or can I get away with just using concentration? Have I started my titration yet? Have I changed my volume of my solution at all? No. So I can get away with just using concentration. Look, it'll always work in moles. You can always do it in moles. You're just going to make a little bit of extra work for yourselves if you don't have to do it in moles, right? So when in doubt, sure, go for it. Do it in moles. But in this case, because we haven't changed our volume, we're not starting our titration yet. We can actually get away with just doing it in units of concentration, in units of molarity. All right, so if I'm just going to leave it in concentration, my initial is 0.58. 0 for my products. What's going to go in the change box for the reactant? Minus X, and for the products will be plus X. All right, so everybody I want y'all to see if you can do this on your own here, but there is one thing we're going to need. I need to go ahead and look up my value for Kb from my constants page. So real quick, let's jump over here. All right, we got acids on top. We got bases on the bottom. So I'm going to look for NH3, my ammonia. 1.76 times 10 to the negative 5. All right, and so I want everybody to take a second and see if they can't finish off to get the pH of this solution. Again, this should be review from chapter 17 here. We want to be really good with working with weak acids and weak bases. All right, so I took my equilibrium boxes from my ice table and plugged them back into my KB expression. So I got x squared over 0.58 minus x equals that KB value of 1.76 times 10 to the negative 5. But because KB is so teeny small, x is going to be really teeny small, and I get to just ignore it in my denominator here, this minus x. So rearrange and I solve for x. I get 0.00319 and some change. And then I take the negative log of that value, and I'm done. What's wrong with this? This is the POH, absolutely, because we're talking about a weak base solution. So look, in my ice table here, x is not hydronium concentration, but hydroxide concentration. So I'm well on my way here, but now I have my POH, not my pH. So I got to do one more step here. 14 minus that POH. I get 11.50. Okay? And right, like sanity check, that checks out. That's a basic pH. I don't want to stop with a pH of 2.5 for a solution of weak base. That doesn't make any sense. Right? So just make sure to take a step back and look at your numbers. Yes, I should have this nice basic pH of 11.5 here. That's my starting solution in my flask. So I'm going to go ahead and put that point in. I don't know, somewhere like right here. Cool. All right, so now we're going to move on to our second region here. We have our weak base plus our strong acid. All right, but we haven't yet hit that equivalence point, so we have an excess of our weak base. All right, we're not yet at that equivalence point. So we're going to add some base, and it's going to react, but I'm still going to be left over with an excess of that weak base in there. I'm going to add strong acid. Is that what I said? Yes, hopefully. Okay. So how are we going to solve for our pH in this region here? Well, now we got to build an ice table to account for how much of our chemical reaction has occurred, right? So we need an ice table so that we can figure out how much reaction. Okay, and now that my titration has started, I'm going to have to be really careful and do my ice table in units of moles. Right? Now that we're changing our volume, we need to make sure to do that ice table in units of moles. All right, so let's go ahead and get this kicked off. $65 milliliters. All right, so we need to build this ice table here. And so we need to know what chemical reaction it is that we're talking about. And I think this might be one of the more subtly difficult points here. We're not going to be talking about our KB reaction anymore. We're going to be talking about our titration reaction. What is the chemical equation between my weak base, my ammonia, and now this strong acid that's been added in here? Okay, so everybody take a second. We were titrating with ammonia, NH3. Finish off this chemical equation here. What is my titration reaction that we're talking about now? All right, what's my other reactant? That HCl that I'm adding in there. Absolutely, right? A weak base, strong acid titration. We're really creative when we name things in chemistry. All right, so then my products here, I just got to know my conjugate pairs. Here's my base. Here's my acid. Remember, bases are going to increase in the number of protons, so that would be NH4, increase in the charge. My acids go down in number of hydrogens, so now I'm just at the chloride with a -1 charge, goes down in charge. All right, so again, this is my ice table that I need to account for each of these components of my reaction. All right, but again, we're going to need to make sure when we do our ice table that it is in units of moles. All right, so in order to get moles of ammonia, I have to remember what we started out with in our flask, 1.2 liters of 0.58 molar solution. All right, so everybody take a second, practice your solution stoichiometry here. Give me how many moles of our NH3 do we have, given our volume and our concentration here? All right, in that solution chapter, we talked a lot about how you take that concentration and turn it into something you can use in our math. That 0.58 big molar is how many moles there are in 1 liter of solution. All right, so then we take our volume, our 1.2 liters, and if we multiply these together, we see that our units of liters cancel out, and I'm left with what I want, units of moles. All right, we play that game all the time. Volume times concentration will give us moles. All right, so then by analogy, how much HCl do we have in moles? That's that one. Yep. All right, so I'm going to take my 65 milliliters. I'm going to convert it to liters, dividing by 1,000. And then I can use my concentration. 4.6 moles are in 1 liter. And I know that it's set up correctly because my units cancel out and I'm left with units of moles. So 0.299 moles of my HCl. All right, and we're going to start stuff off with no amount of product. Like before, our reactants will decrease in concentration and number of moles. My products will increase. Okay? But for this particular ice table here, let me just sort of make note. This was our ice table. How are we going to find X? We're going to, what we've been saying before is that all of our strong will react. Right? This is not a reaction that's in equilibrium here. Every bit of that strong acid that we added will react. So that means I know I will have no moles of HCl left over because all 0.299 are going to participate in this reaction. All right, all of that strong that we've added will react. Now, I can't have more base reacting than I have acid reacting. This is a one-to-one reaction, so that value of X has to be the same across the board, right? So these boxes will be negative 0.299, and these boxes will be positive 0.299. All right, so then to get my equilibrium box, I'm just going to sum everything up from my first two. I have that weak base left over, but none of my strong acid. That all got consumed. And then summing these two boxes up as well, I have 0.299 moles of my products. What's up? Yeah, absolutely, right? So the principle is all of that strong acid is going to react, all of it that can. And since I'm limited by my HCl, then yeah, all of that is going to be used up. All right, so let's take a look at what we're left with here at equilibrium. I have some of my weak base left over, none of my strong acid. I have some of that conjugate acid on the product side, and then my chloride ion here, right? So that's the mixture that I'm left with after this reaction reaches equilibrium. Okay? Now, importantly, the conjugate of a strong acid is just neutral, right? AKA, I do not care about how much chloride ion I have in this solution. I can calculate it, that's all well and good, but in terms of my pH, it's not going to influence my pH at all, right? It's the conjugate of something strong, so it is neutral. Okay? But on the other hand, my weak base is going to have a weak acid conjugate. So I do have to pay attention to my conjugate acid over here, all right? But what I'm left with is a mixture of a weak base and its conjugate acid. And we have a special name for those solutions. What are those? Buffers, right? So just like with our weak acid, strong base, this solution, or this titration right here in this region, we have created a buffer solution, which means that when we solve for our pH, we get to use our Henderson-Hasselbalch. All right, so that equation, and that is on your constants page. This isn't something you have to have memorized. Okay, but pH is equal to the pKa plus the log of concentration of base over concentration of acid. All right, so I want you guys to take a second and tell me what is the base and what is the acid? What numbers go in where? All right, make sure that we can identify what is what here. All right, I'm comparing my NH3 with my NH4 plus. Which one is the base? The NH3. All right, so that's going to go in my base part. My acid, that conjugate acid, is what's going to go in the acid part. All right, and we made this big argument last time about how since you're taking the ratio of these two concentrations, you can actually just leave it in moles because your volume would cancel out anyway. So we're going to put our 0.397 moles over these 0.299 moles of acid. Okay, so that's what I'm going to do for my ratio of my base to acid. Okay. If you're confused about why I didn't divide by the volume, you can go back and watch that video. But again, they're both the same, so it'll cancel out when you take that ratio. All right. But now for my pKa, I need to take the negative log of that Ka value. But I got a problem. If I go to my pKa table, I do not have a Ka. Ammonium is not listed on that acid part. It doesn't have a pKa. All I have is a Kb of ammonia. Right? And so we have to remember this relationship between Ka and Kb for our conjugate pairs, where the product of those two, Ka times Kb, is always that same magical number, 10 to the negative 14. So my Henderson-Hasselbalch equation needs the Ka. I can't just randomly sub in the Kb. It's not the same thing, right? But importantly, I can always find the Ka by taking Kw and dividing it by that Kb value. All right, so that's what I'm going to have to do in my Henderson-Hasselbalch equation. I'm going to take that magic 10 to the negative 14 number and divide it by that Kb that we looked up. Okay, we looked it up before. 1.76 something something. 1.76 times 10 to the negative 5. So that's going to go in the denominator. Oops. Okay, I punch that into my calculator. I get 9.37. 9.3686 rounded to 2 decimal places. Okay, one thing is remember when you're punching this into your calculator, since you're dividing by this number in scientific notation, make sure you put it in parentheses in your calculator. Okay, so we can add this here. We see that our pH drops to 9.37. So now we're sort of in this region right here. Okay, and just like we saw with our weak acid, strong base titration, there will be quite a sharp drop at the very beginning that then curves off as you enter the buffer region for that particular weak base. All right, so our next section here, region 3, is that equivalence point. The equivalence point is when the moles of acid equal the number of moles of base. Right, so you have exactly as many acid molecules as you do base molecules in this solution. That's what it means to be the equivalence point. All right, so we're going to build an ice table to figure out how much reaction has occurred here. Okay, we're going to stick with our 4.6 molar. So but importantly, we got to figure out how much HCl, really I want to say what volume of HCl do we add? We know we got to our equivalence point. How much HCl do we have to add to get there? So what volume of HCl was added? All right, and importantly, what it means to be at the equivalence point is that the moles of acid that you started with initially are equal to the, it's base at this point, sorry. Moles of base that you started with initially equals the moles of acid that you've added. All right, so how many moles of acid base did we start out with? How many moles of ammonia did we start out with? Yeah, right, we did that calculation over here when we did our ice table, volume times concentration. We got our 0.696 moles of our ammonia. That's our initial base number of moles, which means that at the equivalence point, I'm going to have 0.696 moles of HCl. So again, this is a problem straight out of our solutions chapter. Tell me what volume of 4.6 molar HCl would have had to have been added in order to account for that 0.696 moles of HCl. All right, again, can you take this 4.6 big M and turn it into something that we can use in our math? That's the name of the game. What's up? So that's the amount of moles of base we started out with initially. But since we're at the equivalence point, what it means to be at the equivalence point is that's how many moles of acid we have at the equivalence point. So that's how I was able to say 0.696 moles of HCl, because that's exactly how I got that number, is because that's how many moles of NH3 I had. All right, so again, we got to take this 4.6 big M and turn it into something that we can use in our math. When I do that, I know I'm going to have to divide by my concentration because I need moles to cancel out and to be left with volume units of liters. So 0.151, we'll just keep a bunch of digits on there. That's how much HCl I got to add. Okay, so again, we're going to build an ice table here. We're again talking about that titration reaction. All right, and since we're at the equivalence point, these two boxes, my initial number of moles of HCl and my initial number of moles of my acid, of my NH3, these are going to be the same number. All right, that's what it means to be at the equivalence point, is you have the same number of moles of acid as you do base. All right, what's going to be my change number here? What value am I going to use in these change boxes? That 0.696, right? All of that strong acid is going to react. Okay, importantly, it's going to be negative on my reactant side and positive on my product side. All right, so taking a look here, this should check out. We're at our equivalence point. So I have none of my weak base or strong acid in this solution because I've added just enough for them to react perfectly with one another. All right, so what I'm left with is a mixture of my ammonium, my conjugate acid, and my chloride ions, my two products. All right, but again, one of these two products we really do not care at all about. Which one is that? The chloride, right? Because it does not contribute to our pH at all. So the only number that I really have to pay attention to here is the number of moles of my ammonium ion. But this is important because my ammonium ion is a weak acid, right? The conjugate of a weak base. So before we can move on here, we got to figure out our concentration of that NH4+. Everybody take a second and see if you can't tell me what our concentration of that ammonium ion would be at our equivalence point. All right, so importantly, my ice table gave me my numerator, my moles of ammonium. All right, but I still have to divide this by my volume of my solution. My initial volume was that 1.2 liters. That's how much I started out with in my flask. But I've started my titration. I've changed that volume, right? So how much have I added to get to my equivalence point? That 0.15 value that we calculated before, right? That's why we got to know the volume of the HCl that we added, because we got to figure out what our new volume is. Okay, so this gives us a new volume of a new concentration rather of our ammonium, 0.51505 molar. Okay, and again, just to emphasize here, at the equivalence point of our weak base strong acid titration, what we're left with is just a solution of that conjugate acid, a solution of weak acid. Right? So when we're talking about our strategy here, our pH calculation will be that for a weak acid solution. Again, what we learned how to do in chapter 17.
Why aren't we adding the 65?
Because that's a good question. So when we figured out, I lost it. Give me 1 second. Cool. When we figured out how much acid was added to get to that equivalence point, that was the total amount of acid required to get to that equivalence point, starting at the very beginning of our titration, starting at 0, right? So this 0.15 liters right here, this isn't in addition to the 65. This is the total that we've added as we've gone along to get to our equivalence point. Right, so yeah, we added 65, then we went to 75, 85, and then by the time we got to the 151, now we've reached our equivalence point. Right, so our calculations aren't successive. You're always going back to your initial solution with your calculations. You could do it successively and it would just be a huge pain in the butt. Right, so it's easier to just start from your scratch solution, your 0.12 liters of your 0.58 molar solution. That's what we're starting out our calculations with. Okay, so I have my concentration of my weak acid here. So how would I finish this off and get the Ka, or get, well, kind of ruined that. Get the pH. We're going to do what we do for our weak acids. We got to get our Ka reaction. Then we can build our Ka expression. And finally, our ice table to solve it all. Again, this is just our general strategy for a weak acid solution pH that we learned in chapter 17. All right, so I'm going to leave this, for the sake of time here, I'm going to leave this for you all to do at home. It's remarkably similar to the one that we did at the beginning, but we did it for a weak base. But I will tell you that the pH at this point is 4.77. So you have a number that you can check when you do this on your own. Okay, so our pH is now in this acidic region. Okay, that checks out because at my equivalence point, because I started with a weak base, at my equivalence point, the only thing I have in my flask is a weak acid, right? So I have this solution of weak acid at my equivalence point, which is why I have an acidic pH, something lower than 7. All right, so if we put this in on our graph here, now we're down in our acidic region. Here-ish. And again, what we would see in our curve is that that lies in the very middle of this vertical region. Okay, so then my last point here is again my weak base plus my strong acid. But now I'm past that equivalence point. Not only have I added enough acid to react with my weak base, and then some, right? So at this point, what I'm left with is an excess of that strong acid. So because of that, I know my pH is going to be somewhere way down here in this really low pH region, because all I have is a flask full of strong acid. All right, so if my equivalence point was 0.15 liters, let's say that we've gone all the way to 0.2 liters of our 4.6 molar HCl has been added. What is the pH? Okay, just like for these other points on our titration curve, I gotta figure out how much reaction has occurred, because I know I have an excess of strong acid, but like how much of an excess, right? What am I left over with here? All right, I'm gonna be lazy and copy and paste this real quick. All right, I want you guys to take a second and see if you can't fill in this ice table, and then I'm going to kind of quietly fill it in, and you can check up here if you're getting stuck. All right, so volume times concentration gives you moles. Again, we're going to play that game a lot. All right, my volume in liters times my concentration in moles per liter. Liters cancel out. I'm left with moles. All right, so again, all of that strong acid is going to react. So it's negative 0.92. What's wrong with that? I don't have enough acid. That's not true. I don't have enough base, right? I have enough ammonia to react with 0.92 moles of my HCl. So exactly, I have to pay attention to what's limiting here, which is actually my weak base. So that's the maximum amount of reaction that can occur in this flask. I'm limited by how much of that I have. So this is going to be negative 696 moles. This will be positive. Okay. So at the end in my flask, I'm left over with no more of my weak base. That's all been used up in my reaction. But now I have an excess of that strong acid HCl. I have my weak conjugate acid, my ammonium, and my chloride ions. All right, that's what I'm left with at this point in my titration. After my equivalence point is an excess of that strong acid, and then my products, my weak acid, and my chloride ion. Okay, so how are we going to get the pH of this solution here? All right, well, again, one thing that we just really don't care about for calculating pH are these chloride ions. They're not relevant. Okay, so if we just nix the chloride ions here, then we have a mixture of a strong acid and a weak acid. All right, both of them are going to contribute to my hydronium ion concentration, to my pH, right? But one of them is going to contribute way more than the other. My strong acid is going to completely dissociate. So that's going to influence my hydronium concentration quite a bit. Whereas my weak acid is going to influence it only a little bit. Okay? So because of that, we're going to just ignore how much weak acid we have there. Its contribution to the pH is going to be negligent in comparison to what my strong acid is going to do, right? So at this point, the only thing that we have as far as we're concerned for our pH calculations is a solution of strong acid. Right? We just got to pay attention to that excess of strong acid there. So we need to just figure out what the concentration of that strong acid is. Everybody take a second and see if you can't tell me the molarity of HCl in this solution. Say it again. It is 0.224. My bad. Right, so my ice table gave me moles, so in order to get concentration, I got to take that moles and divide it by liters. My volume initially was 1.2 liters, and then I added another 0.2 to get past that equivalence point, right, to my region 4. Okay, so my concentration at this point, probably should have done it, would be 0.16 molar HCl. So how in the world are we going to calculate the pH of a solution of strong acid? All right, this is kind of best case scenario. We don't have to do our ice table or worry about a Ka expression. We just get to use the fact that because HCl is strong, the concentration of HCl is simply equal to the concentration of hydronium. All right, so I know how much hydronium I have in this solution. I have 0.16 molar. So then I get to just take the negative log of that value. And I will indeed get a very low pH. Because HCl is strong, it makes, sorry?
You said it makes the other one strong too?
No, it makes it so that you don't have to like account for how much of this weak acid is contributing to the hydronium ion concentration. We're going to ignore this number altogether when we calculate our pH because we have a mixture of a strong acid and a weak acid. The strong acid is going to be the one that contributes to the hydronium concentration way more than the weak acid does. So we're just going to ignore the weak acid component. So at this point, we're going to say we have a solution of just HCl. That's how we calculate our pH. All right, so to finish out this curve here, we are indeed at a super low value. All right, and we can just finish it off. For our region 4, our pH calculation will be that of a strong acid, since we have an excess of that strong acid. All right, so in chapter 17, we learned how to calculate pHs of weak bases and weak acids. And then we got to chapter 18, and all we did was use that over and over and over again, right? So if you're having trouble calculating the pH at step 1 of our titrations here, you need to go back and review what we did in chapter 17 for those weak acids and weak bases, because that's a fundamental part of how we do our titration. Okay? In the case of a weak base strong acid titration, we start out with just a solution of weak base. Okay? Then along our titration curve here, when we are in region 2 before our equivalence point, we have a mixture of our weak base and its conjugate acid, right? So that's what we call a buffer solution. When we get to the equivalence point, we have an equal number of moles of acid and base of acid that's been added as our base that we start with. So what we're left with is a solution of weak acid, right? Because all that weak base has been used up, so all we have is that product, a weak acid. And then once we get past that equivalence point, now we have an excess of our strong acid. So when we calculate our pH, we're just going to focus on how much of that strong acid we have in solution. And then we can assume that the strong acid concentration equals the hydronium ion concentration. All right, that is titrations. I know everybody's absolute most favorite type of problem to do because they're so incredibly quick. No, they do take quite a long time, all right? But again, we break them up into those 4 regions there, and that's what you want to think about when you're practicing these problems. All right? That's all I got for you.